Here's a beautiful exponential equation. 2 to the x plus 8 to the x equals 130. Now at first, this looks tricky because we've got different bases, but there's a really elegant insight that makes this whole thing collapse. The key to cracking this is getting everything in terms of the same base. So let's look at what we have. The bases are 2 and 8. And here's the thing. 8 is just 2 cubed. That's our way in. So we can rewrite 8 as 2 cubed. Now we need to use the power rule. When you raise a power to a power, you multiply the exponents. But here's what's cool. The order doesn't matter. A to the m, all to the n, is the same as a to the n, all to the m. So let's apply this to 2 cubed, all to the x. We can flip the order and write this as 2 to the x, all cubed. And now look what happened. 2 to the x shows up in both terms. This pattern is screaming for a substitution. So here's where we are. Let's call 2 to the x just y. Everywhere we see 2 to the x, we replace it with y. And just like that, our scary exponential equation becomes y plus y cubed equals 130. That's just a cubic polynomial. Let's move everything to one side to get it in standard form. So we have y cubed plus y minus 130 equals 0. Now we need to solve this cubic. Let's try some integers. By the Rational Root Theorem, any integer solution has to divide 130. Let's try y equals 5. 5 cubed is 125, plus 5 is 130. Minus 130 gives us 0. Perfect. So y equals 5 works. But wait, cubics have 3 roots. Are the other 2 real? Since y equals 5 is a root, y minus 5 must be a factor. We can factor this out using polynomial division. Polynomial long division works just like regular long division, but with polynomials instead of numbers. After the division, we get y minus 5 times this quadratic. Now let's check if this quadratic has real roots. The discriminant will tell us everything we need to know. For a quadratic ay squared plus by plus c, the discriminant is b squared minus 4ac. If it's negative, the roots are complex. Here we have 5 squared minus 4 times 26. That's 25 minus 104, which gives us negative 79. The discriminant is negative, so the quadratic has no real roots, which means y equals 5 is our only real solution. All right, we know y equals 5. Now let's get back to x. Remember, y was 2 to the x, so 2 to the x equals 5. To solve for x, we need logarithms. Let's take log base 2 of both sides. So we have log base 2 of 2 to the x equals log base 2 of 5. The power rule lets us bring that exponent down front. So we get x times log base 2 of 2 equals log base 2 of 5. And log base 2 of 2 is just 1. So this is just x times 1. And there we have it. X equals log base 2 of 5. That's our unique solution. Let's visualize this to see what's really happening. Here's our coordinate system. The blue curve is our function, 2 to the x plus 8 to the x. The green line is y equals 130. Where they cross, that x-coordinate is our solution. And look, they intersect at exactly 1 point. The x-coordinate here is about 2.32, which is exactly log base 2 of 5. This confirms everything we just derived algebraically. Thanks for watching. If you enjoyed seeing how substitution and logarithms work together, give it a like and subscribe for more mathematical insights.